Hello, this is the paper Reachability Analysis of Nonlinear Systems using Hybridization and Dynamic Scaling. I'm Stanley Bach and I'll be presenting this talk. I'll be joining Stony Brook University as an assistant professor in the fall. This is a joint work with Dongshu Lee from Australian National University and Sergei Bogomolov, who used to be at Australian National University and is now at Newcastle University. This paper is about analyzing nonlinear systems using reachability analysis, and in particular improvements to the hybridization process so that error is reduced. The grand vision of these sorts of methods is to enable formal analysis of complex cyber-physical systems. What's shown here is a benchmark model of an F-16 designed using techniques from aerospace engineering, and this was released a couple years ago from our group, and it's a very difficult benchmark to analyze. Looking at formal models of these types of systems, you come to realize that there's two types of behaviors going on, discrete behaviors and continuous ones. And you can model this using something like a hybrid automaton, such as the one shown on the bottom here. So this is a particular aircraft maneuver that's going on, and there's 4 different control modes. And in each of the control modes, there's a sequence of differential equations that tells you how the continuous continuous states evolve. So the sort of vision is that if we have powerful analysis methods, we can prove properties about these sorts of systems, prove stability, prove that there's collision avoidance, and so on. And this paper is a small step in this direction. There's 3 main parts of the talk that I'll be going through. There's reachability analysis, hybridization, and then finally our contribution, which is dynamic scaling. So what is reachability analysis? Reachability analysis is, you can think intuitively of as set-based simulation. So given the problem is basically given a system model, such as a set of differential equations or a hybrid automaton, and some initial set of states, and some stopping conditions, such as a time bound, and optionally an unsafe set, reachability analysis strives to produce 2 things. Either the set of states that the systems can enter, or if you have an unsafe set, it'll try to intersect the set of states that the system can enter with the unsafe set. So is an unsafe set ever reachable starting from the initial set? The reachability analysis method that we analyze in this paper is flowpipe construction. So flowpipe construction you can think of as a set-based simulation, as I alluded to before. So instead of sampling from the initial states and performing simulations of the system, flowpipe construction strives to take the whole set of states and propagate it through the differential equations, and if you have a hybrid automaton, through the different discrete control modes. Simulations are probably the most common used method to analyze these types of systems, but they're insufficient because you're never going to sample all of the points inside the initial set. It's usually a dense set of states with infinitely many points, and so you might miss cases that are actually unsafe using a simulation-based approach. There's also issues of external disturbances or model error that come into play, which makes simulation insufficient and sort of leans towards flowpipe construction. However, the problem with flowpipe construction is it's often difficult to perform, especially when the dynamics are nonlinear. Reachability analysis looks something like this, where if I have this simple 2-mode hybrid automaton, where in the left mode, the initial mode, the dynamics are rotating clockwise around the origin, and in the right mode, it's a move right mode, which means the dynamics just move to the right. So this is a simple 2-dimensional system with a discrete switch between the modes according to some condition. So in this case, the condition is that x is greater than 0. So if my initial set of states is this green box shown on the right, and we're doing discrete time reachability analysis, we might be interested in computing something like this set of states shown up here. So you can see that first the dynamics rotated around clockwise around the origin, and then as soon as you cross the threshold, it switched to the move right mode. This is not always so simple, so here's the same situation with sort of a modified condition of when to switch to the move right mode, and you can see that now there's sort of multiple steps that intersect the guard. It intersects the guard at multiple points in time, and in the successor mode there's multiple states. So the sort of reason I'm showing this is to motivate the fact that reachability analysis involves geometric set operations. And so if you want to perform flowpipe construction, reachability analysis, you need these operations to be possible and efficient and hopefully low in error. So you need ways to advance time through the differential equations. You need ways to check if intersections are empty to see if the guard is reached. If you have external inputs, you need to do what's called a Minkowski sum operation. You need to be able to compute intersections. If you saw in the last mode, we did not the whole set crossed the guard condition at the same point in time. And perhaps you also want to do aggregation using convex hulls, or you want to do some sort of termination checking, which involves subset operations. So this paper is not about all of these operations. Instead, it's about specifically the advanced time operation when the dynamics are nonlinear, and we also have some contribution for external inputs or disturbances with the Minkowski sum operation. So what is hybridization? You can think of hybridization as repeated local linearization. So a nonlinear system is really a nonlinear system locally behaves like a linear system. So the idea is, if you want to analyze a nonlinear system, you can repeatedly perform a linearization process, and then you'll get an approximation of the dynamics. And if you take into account the difference between your linearization and your nonlinear system, then you'll get an over-approximation of the dynamics, which means that you compute a larger set than what's actually reachable, and that's still useful for verification. So a nonlinear system is something like the van der Pol oscillator, which is shown here. So this is a two-dimensional system, so it's sort of nice to visualize, and this is the running example we'll use in this talk. If you have a set of nonlinear differential equations, you could sample at every point in the state space and construct a vector field, such as what's shown here. And it's maybe a little bit tricky to see what's going on with the vector field, so it's often useful to simulate the system as well. So if we randomly pick points in the initial set and we simulate according to the differential equations, we can see that sort of no matter what point you started out with, you end up on this sort of limit cycle behavior. So this is the behavior of the van der Pol oscillator. So the hybridization approach to analyzing this type of system would say that rather than treat the whole space as a nonlinear system, we'll instead divide it up into pieces. In this case, there's 4 pieces on the right. And we'll come up with linear approximations within each of those zones. And we can divide this up arbitrarily. Here I've just shown 4 modes. And so it's not actually enough to just do linearization. This will give you an approximation of the dynamics. But if you want an over-approximation, you have to add some external noise or disturbance to account for the fact that the nonlinear system is not going to be exactly equal to any of these linear systems, but it will be close. So there's ways to do this to come up with how much you need to modify the linear system. And so what you end up with is a sequence of noisy linear systems. In the sort of automaton formulation of this, you can see that we started out with an original continuous nonlinear system, and we then ended up with this sort of hybrid system now where we have linear dynamics. So the BU term here corresponds to the noise. And the linear dynamics are different within each mode, and you can imagine we can repeat this to reduce error. So the pros of this type of hybridization analysis, this is called static hybridization, is that you can reduce error by using smaller boxes. You can, instead of using 4 boxes, you could, imagine using 9 or 16 or any number you need, and you can get better and better error. But the downside of this approach is that the number of modes becomes exponential in the number of variables. So if we had a 10-dimensional system, if we needed to split along each state, we would have 2 to the 10 discrete modes, which is over 1,000. If we had 20 variables and even just splitting one time along each variable, you would now have 2 to the 20 modes, so over 1 million modes. So it doesn't sort of scale well in terms of the number of variables, but it might work in 2 or 3 dimensions. Another problem that's sort of not really often considered because the first one's sort of bad enough is that when you use this type of static hybridization, you have to compute geometric operations at the mode boundaries. You need to check if the set of states you're propagating through the differential equations is now in another mode. And then you need to compute intersections too. So that's often error prone. So to motivate a different type of hybridization analysis, we'll go back to the reachability computation problem. So when you're doing reachability computation, you're starting off with some initial set of states here. So here we'll say that the red set is our initial set. And then we propagate this through the differential equations, and we are interested in computing what's called the reachable set. So what's shown here is that the gray set of states is actually the reachable set of states, sort of like the time invariant states that the system can enter, where the states in red is what we call the current set. So at one particular point in time, which states are reachable. So with dynamic hybridization, it's a different way to do this piecewise linear approximation. Instead of dividing up the state space, what we do is we sort of track the current set as it goes through time. So originally you had this nonlinear system with some initial set, and we'll come up with a linear approximation near that initial set. And then as we propagate through time, we can come up with a new model that's around the current set of states here. And so the noise linear models sort of have this overlap property, but they're locally tracking the set of states that's reachable. So in the automaton view, now we take this original continuous nonlinear system and convert it into this dynamic hybridized model. And so here we've actually, we have a different linear system in each mode, but we've added also a time variable to determine when to do this switch to the next mode. So for some time, this is the linear dynamics we'll use. As soon as the time exceeds some threshold, now we have a new set of differential equations, and so on and so on. So the pros of this type of approach is that the number of modes doesn't depend on the variable. You don't have an exponential number of modes depending on the number of variables, so you can do this for higher dimensional systems. It only depends on your time bound and the step size. And another important property is that you have time trigger transitions. You don't need to check for intersections to proceed to the next mode because the whole set transitions at the same point in time, so you don't have to compute intersections. That's very helpful. The downside is that we no longer have this error control property. The error really depends on the linear region size, and you cannot fully control that too. So I'll go into that in the next slide, but really what I want to emphasize here is that the contribution of this paper is that we can reduce the error in dynamic hybridization, which was not possible beforehand. So what is this linearization region? So if we go back to the image we had before, the linearization region is the part where your linear model over-approximates the nonlinear differential equations. And so this linearization region has to encapsulate at least the current set at one point in time. It actually has to be a little bit bigger. So if we had something like the van der Pol oscillator, and so this was one frame of the animation we had shown before here. So if the red set of states is the current set, the sort of smallest linearization region you could even consider would be this blue box. Actually, it has to be a little bit bigger, but this is sort of a very large region. There's no direct way to sort of split this into smaller regions in the dynamic hybridization process. So the way we strive to reduce the error is using this process called dynamic scaling. So what dynamic scaling you can think of intuitively is it's modifying the dynamics without changing the reachable set. So how can you modify the dynamics without changing the reachable set? So recall reachability computation, we had this van der Pol oscillator before, and this will be our running example here. So what types of modifications can we do that will not change this gray region, the reachable set of states? So the analogy I like to use here is imagine you're running a marathon. So if you're running a marathon, the reachable set of states you can think of as the path on which you ran. And so the whole motivation, the sort of key insight with dynamic scaling is the path that you run the marathon on is independent of the speed that you're running. So you could, for example, run the marathon twice as fast, and you'll still cover the same set of states here. And so this is what we call double scaling, right? So if you look at the plot on the left and the plot on the right, they're moving at different speeds, but the reachable set of states is the same between them. So if the left side has a safe, if the reachable set doesn't intersect on safe states, the right side won't either. So that's useful. It's not really helpful for computation, but we can think of what other types of scaling we can do. So another type that you can do is what we call here quarter scaling. So here in the green region, what we've done is we've slowed down the dynamics. So in this sort of just small part of the state space, the dynamics goes at half the speed as it moves in the other ones. So again, in the marathon analogy, you could imagine if you're running a marathon and you slow down as you approach, you have somebody cheering you on, you want to wave hello, you can slow down, but you're still going to run the same path. Another type of scaling that's possible, this is sort of like a continuous scaling, is distance to line scaling. So here, as the reachable set of states, as the current set approaches this dotted line, it slows down, and as it's further away, it speeds up. And so again, this you can think of like, let's say the dotted line is the finish line or something. You get more tired near the end of the race, let's say you slow down. You're still going to cover the same path. So now it's like a continuous transformation. At each point in time, you're changing your speed. But again, the reachable set of states, the gray set of states, doesn't change. Another observation is the scaling need not be done at every point in time. It can be a function of the time as well too. So here we have on-off scaling. So just like quarter scaling, we slow down when we're in the green region, but only when it's only sometimes. Again, the reachable set of states in this case doesn't change. And so this is useful because it says that you can apply different scaling at different times in the system, and again, it doesn't affect the reachable set of states. So what type of scaling do we want? So dynamic scaling doesn't change the reachable set, but what it can change, and maybe what you've seen in the previous slides, is that it can change the current set, the red set of states. And that's really what's used to determine the box linearization region. And so the key idea that we use in this paper is to use scaling to make the box linearization region smaller during the dynamic hybridization process, and then this will impact the error of the overall computation. So what we end up using is something called flattening scaling. So flattening scaling, what it tries to do is flatten the reachable set in time. And so what's shown here is that, again, it's similar to line scaling, we take the current set and then we'll scale we'll multiply the dynamics by the distance to the black dotted line. And so the points that are sort of behind in the reachable set will speed up, and the points that are in front will slow down, and so everybody will sort of end up at the same distance from the line. And then we'll combine this with an idea, with the on-off scaling idea, that we can change the scaling at over time. And in particular, we'll change it at every point in time to always be sort of in front of the reachable set. And so let's see what that looks like. So here the scaling process is changing over time, but it's always, if any state ever were to get ahead, it would slow down because it would be closer to the line. And if any state is behind, it would sort of speed up. And again, if you look at the reachable set here, it's the same as it was before. It hasn't changed. But if you look at the current set, it gets very small. And so that's really good, because now the linearization region that you use can be very small as well too, and it'll therefore have very, very low error. There's other concerns in the paper that I'm not going to go into too much detail here. I'll just mention briefly. So the first one is that dynamic scaling makes the differential equations more complex. So this affects linearization error. So linearization error refers to that it's not exactly a linear system that you're converting it to. It's a noisy linear system. So you have to figure out how much noise you need to add to it. And this is essentially a global bounded optimization problem that tries to optimize the difference between the linear and nonlinear dynamics. So if your nonlinear system is more complicated, this problem becomes harder. And so with the solution that we do, it becomes harder, so it's possible you have over-approximation error from the optimization process. So the solution we use in the paper is that we try to use both the scaled and unscaled dynamics and end up using the one that has the smaller linearization error. So we'll try both and use the one that has less error. Another thing we do is we notice that dynamic scaling actually takes a little bit of work, possibly because the optimization problem is more difficult, and we also try both of these approaches. And so it's not really necessary to do it at every step. Instead, we do it every n steps, where n is maybe every 50th step or something, and that seems to produce a good outcome without having too much computational overhead. And so the last thing I'll mention is that I sort of mentioned it before, was that the linearization region, it's not exactly just the current set. It has to be larger than the current set. It's actually a linearization region for some interval of time. So it needs to encapsulate both the current set at the beginning of the time interval and the current set at the end of the time interval. And this is actually not enough too. It has to encapsulate all the reachable sets between these two time steps. So the way to do this in linear systems reachability analysis is you do something to take into account all states in some time interval between two time steps. Use what's called an approximation model. So you don't actually want this blue rectangle. You want a slightly larger rectangle, and that slightly larger amount depends on the approximation model. And so we've actually in the paper have an improved approximation model for refined systems, so that we can have better error bounds when we do hybridization. We have an evaluation on many systems, and I won't go into the details here except to point out that the number of dimensions ranges from 2 dimensions to 30 dimensions in our evaluation. We used a large number of oscillators because those are nice, because this technique works best when you have a small set of states that will be approached by the system. For example, you have a stable system, but they approach it at different times. So oscillators are sort of good in that direction. But we have a couple other biology systems too. So we compare our tool here with Flowstar, and we spend a good amount of time doing parameter tuning with Flowstar. So that's why you see the parameters here in the table. But sometimes our technique is faster, and sometimes there are systems where Flowstar is faster too. So this is sort of promising, because Flowstar is really it's a Taylor model-based tool for integrating nonlinear systems, and we can still beat it for some systems with 20 or 30 dimensions where Flowstar sort of times out. So this is sort of a nice result. There's also plots that are shown in the paper. So on the left side here, this is with dynamic scaling. You can see this nice sort of tight plots. Whereas now, without dynamic scaling, you can see that there's sometimes blow up, and this is sort of expected due to the linearization error. And so for some of these systems, Flowstar doesn't compute the reachable set either. So that's all I wanted to cover in this talk, and happy to answer any questions. Thank you for listening.